In previous videos, we looked at the frequency p-value and compared it with Bayesian posterior. And now what we're going to do is compare the Frequentist 95% confidence interval with the Bayesian 95% credible interval. And when did this, said that it wasn't a direct comparison of frequentism versus Bayesian per se, but rather a comparison of these two specific methods. And now what we're able to do in this case is a fair head-to-head comparison of these two approaches, because they're both trying to do the same thing, and that is create an interval. So we'll begin with the Frequentist 95% confidence interval. And the thing to bear in mind with the 95% confidence interval is that it defines a process for making intervals. So if we think about our IQ example, there's the mean IQ of the IB students, and we've got a process that generates intervals. And so I could generate a very large number of intervals, and I've just shown some of them here. And the whole idea is that as the number of intervals approaches infinity, the proportion, the relative frequency of intervals that actually straddle the true mean, that proportion of intervals that straddles the true mean approaches 95%. The key thing to remember is that mu is fixed. We could go out there and get the records of all the IB students, determine their IQ, and determine what that mean value was. In contrast, the intervals can be thought of as random variables. Every time one did the experiment, one would get a different sample and a different interval, but in the long run, 95% of those intervals would straddle the true mean. In terms of the mathematics behind the calculations, you're probably familiar with those. There it is there. Take the average value plus or minus z times the standard error. So the average value was 111. There's the appropriate z value. Standard deviation we assumed was 15. Sample size was 9. That gives us, for this particular experiment, this particular interval. What can we say about this particular interval? What's rather important is what we cannot say. We cannot say that there's a 95% probability that the mean lies within this interval. In fact, this statement is exactly backwards from reality. What this statement implies that you've got a fixed interval, and there's a 95% probability that this mean is some random value that 95% of the time lies within the interval. And that's completely backwards. Need to reverse these. It's the mean that is fixed, and the intervals are random. 95% of the time, they will straddle true mean. The next thing is a little bit more subtle. You can't say that this particular mean has a 95% probability, excuse me, this particular interval has a 95% probability of straddling the true mean. And the reason for that is that what I've shown here is a whole bunch of confidence intervals, most of which straddle the true mean, one of which didn't. But you only do the experiment once. You only get one particular value. In this case, we got this particular value. But all we see is this value. We don't know whether this is the interval we got, this is the interval we got, or we were unlucky and this is the interval we got. Once we have this interval is fixed. Once we've got it. Mu is certainly fixed. So we've got two fixed items. It really doesn't make any sense to speak of probability. So, given what we can't say, why bother? Well, what we can say when we've gotten this interval is that one of two things has happened. Either, in fact, that it does straddle the true mean, or alternatively, does not straddle true mean. Now, given the process that we've undertaken, the probability of this thing not straddling the true mean, that would be a rare event. An event that in the long run would occur only 5% of the time. And so what we're going to decide is that, hey, I don't believe in rare events. I'm going to take a guess that this is what's really happened. And it's not really a wild guess because we know that we've gone through a process. We arrived at this interval by a process that would give us intervals that in fact did straddle the true mean 95% of the time. So that's the confidence interval. Now let's move on to the Bayesian credible interval. So there's our run-jags function. There's our model. There's mu. We create an object called results. We print results. And by default, it gives us the 95% credible interval. So what's happened is, on its random walk, JAGS has generated 60,000 values of mu, and 95% of them lie within this range. So that's wonderful. It gives us what we've got, what we want. The probability of mu lying within this range is 95%, because in fact, 95% of the values did lie within that range. Of course, the price we pay for it, as we'll see, is we're dealing with beliefs. So let's make some more comparisons between the Bayesian and the frequentist. The first thing I would say is the Bayesian is more direct because it gives us what we want. A 95% probability that the mean lies within these two values. In contrast with the frequentist confidence interval, it's very indirect. We go through this process. We know that one of these two things has happened. We assumed it wasn't a rare event, and that gives us license to say that the interval does in fact straddle the true mean. The price that the Bayesian pays for this is that the Bayesian is dealing with belief. What the frequentist can argue is that they have a really good process. They've got a really good process in place that will yield results that are going to give the correct answer 95% of the time. So that the frequentist might argue that if the goal is error control, frequentism is the correct approach because it does give us this very high long-run probability of making the correct conclusion. Now, this is kind of what goes through my mind, and I'm not 100% sure that it's correct, but I think it's informative to think about a 60% credible interval versus a 60% confidence interval. So you got the Bayesian versus the frequentist. So we've got this object called results. I've added a bit more code. So add summary to results and ask for a 60% credible interval. And there is my 60% credible interval. 60,000 values of mu. 60% of them lie within this range. Everything's wonderful. 60% probability that mu lies within this range. How about a 60% confidence interval from the frequentist? Well, I have a lot of trouble with that. I have a hard time wrapping my head around it when I come back to this logic. Why did the 95% confidence interval work? It worked because there's only two alternatives. And the second alternative, that it doesn't straddle the true mean, is a rare event that only occurs 5% of the time. But if we crank it down to a 60% confidence interval, then there's a 40% probability that it doesn't straddle the true mean. Therefore, we're no longer dealing with a rare event, and therefore this logic no longer applies. So to me, when I think about it, the Bayesian has the obvious advantage that it's direct. It gives us exactly what we want. A 95% probability that the mean lies within some range. The frequentist is less intuitive, it's more indirect, but the frequentist might argue that their method is superior in terms of long-run error control.